more efficiently in the geographic terms, it also enables electricity use to be shifted over time, for example, from period of peak demand to those of off-peak demand. So, our topic today is recent advancement in smart grid and renewable energy. We have with us Dr. Sushanta Doctor, Head of the Department of Electrical Engineering, Dr.B.C.Roy Engineering College. Shall I request you to kindly address the program, sir? Sir, you are not audible, sir.
Just sorry.
Yes, sir.
Yeah. Good afternoon to all present. Respected speaker, Mr. Sumanta Basu, Joint General Manager, L&T-MHI Power Boilers Private Limited. Respected Principal Sir, Vice Principal Sir, Register Madam, colleagues and faculty of different colleges and postgraduate students. It gives us immense pleasure to welcome all of you this afternoon to the online faculty development program on recent advanced smart grid and renewable energy, jointly organized by the Department of Electrical Engineering, Dr.B.C.Roy Engineering College, Durgapur, and the Institute of Engineers, Durgapur Local Center. This program would include number of advanced topics related to the field of smart grid, studies on multiple power quality, event monitoring, design and control of interfacing converters for microgrid application, power quality improvement in grid connection PV systems, and evolutionary algorithm application to renewable energy based on power system. I hope that everyone would take the results of this program to enrich their knowledge and skills. We wish all 5 fruitful days of interesting and beneficial program. We have amongst us 7 speakers who are highly qualified and possess vast knowledge and experience in the different fields of electrical engineering. I welcome you all once again to the FDP and hope that you all will have a great time ahead. Thank you all. Thank you, sir.
Thank you, sir. Now I'll request our principal, sir, Dr. Sanjay S. Pawar, to kindly start the session, sir. Thank you.
Yeah, my voice is fine. You're able to hear me? Yeah. Good afternoon to all. Good afternoon to today's speaker, Sumanta Basu sir. It's my pleasure to host you here on this a special topic, which is more interest to us also, and we would like to dig into much more into with your help from L&T point of view, and many other speakers that are involved. The topic really is very interesting for us, and specifically though we are working from theoretical concept point of view, but I think I had been discussing one of it with faculty members also. If can we have some kind of a models available with respect to the renewable energy, and how, sir, you can help from industry point of view, so that may not be a practical perspective exactly, but at least the understanding of the faculties and students will be there from the demonstration point of view. And of course, with respect to this, people will be able to join the research activities related to this one, smart grid. Of course, as Professor Kamalika was saying, there are so many things involved with respect to the smart grid, and we have also seen if the grid is not a smart, how what is called as a effect happens into the grid failures and how it can get separated. Though I'm not from that field, but I still understand maybe from how technology and ICT can be involved into improving the quality and efficiency of such systems. As far as renewable energy, the specific areas, multiple options are there. I still remember one of the example or the advertisement, which I'm speaking at many times from the various occasions, that Mahindra was trying to launch one vehicle, and then they invited, I think it was a case in UK, and then they invited a group of people to dance on a floor, and with a very good music, and that dancing of a floor by around 40 to 50 people generated energy and electricity which was used for the same purpose. So there will be many cases, though the practically and industrial utilization and its research activities would be totally different. But to create an interest, similar such kind of an experimental basis, I think we can start. I think I had already asked our HOD, Professor Sushanta Datta, to work, and it's an open challenge for some of our faculty members also to get involved. The funds involved, the ideas, maybe we can take a help from the industry people. The funds involved will try to ensure to support from the institute as well as joint collaboration and research point of view. And I'm sure a lot of funds are available also in the area. Only the thing is that to go into the detail, identify the areas and work and prepare a prototype model and so on. I'm sure this FDP, of course, after the FDP, the continuation in the research activities, not only from the publication point of view, but really generating and giving back to the society point of view, the students and faculty will take interest from that point of view. I welcome once again to all the attendants, people who are attending this, as well as to our speaker. And I'm sure this will be quite interesting to all of us. And so on. Thank you.
Thank you, sir. Before we Thank you, sir. Before we start with the tech talk by our speaker today, we have Mr. Sumanta Basu. I'd like to give a short intro of him, though he doesn't need he's having a vast experience, but let me give a short intro to about him. He's having more than 32 years of experience in organizations like NTPC, DCM-Shriram, L&T Mitsubishi, heavy industries, over 30 projects in coal-based thermal power projects, engineering, and biomass-based renewable energy resources, with expertise in consulting and project engineering of electrical and automation system, instrumentation system, and advanced real-time monitoring and process control based on artificial intelligence, tools like IoT, MPC, IMC, performance diagnostic and optimization of power generating system, asset management, data analysis, business analytics. He holds patent on aerofoil design for airflow measurement and has publication on International Journal IEEE, Journal of Control Science and Engineering, International Journal of Innovative Studies in Science and Technology, International Journal of Mechanical and Applied Engineering. His strong skills are strong technical knowledge over domain expertise. His main operations are in process mining, business process and performance analysis, criticality assessment, risk assessment, cost management, inventory management, asset strategy development and optimization management, project management, innovation, and improvement digitalization. And he has served one of the major key industries like power sector, chemical and fertilizer, and renewable energy. Sir, we are very happy to have you in this platform. We have a lot of faculty members as well as uh, PhD scholars with us and industry people with us who have joined to listen to you, sir. Sir, the platform is yours. Kindly take over, sir. Thank you.
Yeah, thank you, Dr. Kamalika. First of all, I convey my thanks and gratitude for inviting me and considering me suitable for the all learned persons in front of my virtual screen. Your principal, your this, head of the department, electrical, Dr. Datta, and you and all others who has participated in this program. First of all, this with my heartiest gratitude to all of you, I must convey that being in the industry for last 32 years, uh, so I would suggest everyone that don't forget what you were teaching or what the students are studying. Okay, so it's the deep learning and correlations of the fundamentals and the applications to the industry. Whatever we are basically in the industry or the application engineering are being performed or being innovated by you people only. We are just conveying or proceeding with your knowledge, with your innovations, with your suggestions, and taking it to the industry to solve the problem. This is the background why everyone in the industry are debted to the all learned persons, faculties of various institutes. So you must be aware of this national smart grid mission launched by the Government of India, Ministry of Power. Okay. So it was launched in 2015, and the objective was to have to deliver a quality, reliable, and cost-effective power to all the citizens of India. So whether it is in cities, metro cities, village, rural areas, so everything, everywhere. So that was the objectives. Now in our country, you know that the generations are, it's a mixed type of generations. There are fossil fuel fired generators, there are solar, there are your hydro, gas fired. So all is a mixed generations. So as of now, if we talk about as on today, there are total 409 gigawatt of power generations in our country. Out of that, these 166 gigawatt is the renewable energies, including large hydros. So this is around 42% of it leads to the 42% of non-fossil based power generations. As Honorable Prime Ministers of India, that he has already visioned and declared that by 2030 there will be the renewable energy target is 500 gigawatt, which will be around the 62% of our total power generation requirements by 2030. And the CEA, that is also one wing of Government of India, Ministry of Power, Central Electricity Authority, they have predicted that by 2030 total power requirements will be around 820 gigawatt. That has been projected. So out of that, 500 gigawatt will be non-fossil based. These are the background of this national this smart grid measurements, monitoring, or whatever all components used to be used to contribute. Let me share these presentations I prepared for today's purpose. Just a moment. Are you able to see the presentations?
Yes, sir.
Yeah. So this is the what I told about this smart grid mission. That was by Ministry of Power Office memorandum dated 27th March 2015, and has been operationalized in January 2016 with a dedicated team. So the structures of these is basically a 3-tiered structures. Uh, The tier 1 is chaired by the Honorable Minister of Power, Mr. R.K. Singh, and in tier 2, it is chaired by the Power Secretary, Mr. Alok Kumar, uh, and who is being guided by the CEA. And tier 3 is the different consultants, the Smart Grid Knowledge Center, and the project management units. Those are interacting with the policy and planning monitoring unit, cyber security management unit, R&D center, and your training development and project feasibility studies center. And the state level, it is by the your all DISCOM, maybe the distribution utilities, and especially as smart grid sale, and of course all these 3 tiers, including the state level, are working towards for the betterment of our society, that is on all the consumers. Uh, so this is the structures of the National Smart Grid Mission. So since we will be discussing about all those things in the subsequent slides, so I thought that it is better to know that how it has been originated. The benefits discussed in those committee was mainly with respect to the customers, focusing customers, regulators, and utility companies to address the optimized asset utilization, minimize the transmission and distribution losses, the peak load managements, increased grid stability and visibility to the customers, self-healing methodology, and integrations of the various energy sources, whether it is the battery, hybrid energy sources, then your hydro, then fossil, then solar, so all those things. To achieve higher accessibility to the electricity, improved power reliabilities, backup power requirement, minimizing, improved power quality, and multiple options, that is a demand response, then demand settlement mechanism, and which is focusing mainly on the economic aspects of doing business in the power sectors. Uh, uh, the main functions, or what are the difference between the conventional power systems and why we have gone for this smart grid. So the basic objectives shall be there, then focusing those objectives, the advancements, what are the technology required, so all those things has come up. So the drivers for the smart grids are mainly the accommodating the distributed generation systems, renewable energies, and microgrid, and to minimize the disturbances on the power grid, then region-wise and even country-wise transmission of power. Means you must be knowing that we are integrating with Bangladesh, Nepal, Bhutan, even thinking about for the Sri Lanka also. So neighboring countries also, the networking. This then of course government has worked out the capital cost requirements for these smart grid missions. So a real smart grid that mainly we understand that it's not only the grid automations or simply the demand response. It's includes all together. It's smart metering. For the smart metering, there are the separate committee under the Power Finance Corporation who has given the loan to all the discoms to revive the metering system and the distribution systems. I mean, all the transformers, all metering systems. It's a 33,000 crore of rupees sanctioned by the government for only reviving the smart metering. So you must be now understanding what are the focus of the governments. Okay, so the smart metering, demand response, real-time ratings, energy storage systems, and integrated smart grid controls. Okay. Now, for this case of discussions today, this is the background, the way we are working towards or discussing for this advancement on the smart grid. I will mainly emphasize upon your all technical aspects which are being now under R&D or which are being applied on a experimental basis, and still it is in the development stage. What are the characteristics of the smart grid? So it aims at large deployment of load prediction and forecasting using AI/ML tools. AGC means the automatic generation control. DSM, it's a deviation settlement mechanism. That is also the mechanism set by the government Ministry of Power. Then the integrating all the microgrids, then using converter with synthetic inertia in distributed and network manner, rerouting the power flows, change the load patterns, improve the voltage, and correct network in a matter of seconds. I will tell you that how it affects the entire the power grid of our country. And provide advanced visualization tools to manage the power system network. We call it digital twin. Digital twin is nothing but that it's a virtual replica of the physical systems, and it has the capability of real-time simulation, monitoring, prediction, asset management, so all those things. So this is the combinations of the 2D, 3D systems and applying the various AI/ML tools. Real-time self-assessments to detect, analyze, respond, restore grid components, provide real-time information to the consumers. It's a economically selecting the most efficient power sources. Demand response to shift peak demand. So this is the terminology that nowadays it's a hot topic. It is called the flexibilizations of the power system. So maybe in another 2 months, there will be a new notifications will be published by CA for all the power generating companies and the grid controls of India for managing these peak power system instability. Minimize interruption time, identification of problematic devices, means fault identifications, communication with local or remote devices to analyze faults, low voltage, poor power quality, overloads, and other negative aspects. Renewable integration, that is a very, it's a $1 million questions, how the renewable energy, how the renewable energy will be integrated. So this is the, what are the characteristics of the smart grid? So it aims at large deployment of load prediction and forecasting using AI/ML tools. AGC means the automatic generation control. DSM, it's a deviation settlement mechanism. Then its stability gets affected with renewable integration. As you know, the more and more penetrations of the renewable power on the network, it leads to the instability of the power systems because it's have only the active power. There are no reactive powers. Uh, so that is also a challenge for the smart grid. It will also require big data analytics, cyber security measures to be adopted at various level. There is a standard IEC 62443, which deals with the cyber security of all the monitoring and the control systems of in the domain of power generations. You must be aware that a few days back, this All India Institute of Medical Sciences in Delhi, they suffered a cyber attack, and it stalled the entire activities on all the outpatient department of AIMS. So it's basically AIMS got paralyzed with respect to the patient handling. Similarly, the case of power generation companies, you must be remembering that almost 1 year back, the same cyber attack happened in Andhra Pradesh also. And smart and secure distribution network development that integrating all the various sources of energies. So this is a basic schematic of these power systems with a control. The LC1, LC2, LCA, and these are mainly the load centers. There are transmission line, and there are generation centers. So these generation control systems is nothing but that this is the various generating sources. It may be coal-based, mainly it may be nuclear, it may be renewable energies, it may be your energy storage systems. So all those things. So now, if you see the entire country's network, you will find that that a northern region, northeastern region, western region, south region, central region, all are of various sources are connected with each other. So disturbance in one places in one region affects the generations in other regions. So the real islanding, still we are yet to achieve reliable real islanding of the problematic sector. So that's why this I told about that the load predictions and fault identifications. So based on the artificial intelligence model, so it's a forecasting before it happens. So those things are gradually coming for deployment in the this Indian power system network. So you must be aware that during COVID time and after that also there was 2 incidents where the entire countries, the lighting load came down, okay, as per the appeal of Prime Minister of India. So though the lighting load comprise of very small percentage of total grid load, but still before going to that, a lot of simulation studies happened, so that by switching off the lighting loads of entire country doesn't destabilize the power system network. So now for the power system network, we understand the stability of a network is by the power qualities. It's a voltage, it's a phase, it's a frequencies. So these are the main three factors which define the stability and quality of the power systems. Now, for the grid frequency, this is if you see this the blue line, this is the normal the frequency response characteristics of all the generating stations. Okay. Now, towards the improvement of the grid stabilizations, the power generating companies has been told to modify their frequency response characteristics with a much wider to take care of much wider range of load variations. So it was then the next step is that red line, what you were seeing on the presentations, that this is the modified frequency response characteristics. So you see that it passes through the 0, 0 line. Okay, so that means that there is no ripple in the power system frequency has been considered here. Okay, so that means if there is any small variations in the frequency, there will be always the oscillations in the power generating stations. Mainly if it is a steam turbine driven generator, then there will be always the variations of the governors there. If it is a renewable energy driven final converter, so there the frequency control techniques also has to be implemented to handle these small frequency variations. So this is called the ripple effect. Now, based on the experience, this also get modified. So it's modified to accommodate the disturbance because of the ripple. So it is plus minus 0.03 hertz. So our power system frequency band is 49.95 to 50.05. Okay, so to accommodate any variations of load if the frequency varies like this, so it is a plus minus 0.03 hertz dead band has been given to eliminate that ripple factors. So this is at present the frequency response characteristics being followed by the power system network in operating in India. So so this is a typical frequency response during a disturbance happened in the power grid. So if you see the minimum when such disturbance, suppose frequency dropped from 50 hertz or 50.02 hertz to your less than 50 hertz, then the machine's system inertias that governs the rate of change of frequency declining. Okay, so the first the grid is supported by the system inertias. Okay, and then if the frequency variations, the dip in the frequency is much more, then it comes to a minimum level. It is called the nadir frequency, and from there all the power generating stations that comes to the droop control modes, where it tries to restore or stabilize the frequency towards 50 hertz. But because of the limitations in the system inertias and the limitations of the inter-area connectivities or area response characteristics, it cannot attain or restore back to original 50 hertz. So this state is called the quasi-steady state of the frequency response characteristics. And finally, it settles down to a value, frequency value with an offset, where you need some secondary controls to assist to bring back the frequencies to the national frequency. So the entire frequency response during any disturbance happened in any region in India. So it's divided into three sectors: inertial response, primary control response, and secondary control response. So primary controls, the timing has to be within 30 seconds. It has to bring back the frequencies to within 30 seconds to normal. If it is not available, or if it is not able to bring back, then secondary controls has to be there automatically. There is no manual interventions there. The secondary controls, as I talked about, there is the automatic generation control. AGC has to be there, which takes into account the spinning reserves of different areas in the country, whether it is immediately, suppose the disturbance happened in the southern region, maybe in the eastern region there are some spinning reserves available, so immediately it has to support for this to southern regions to stabilize the frequencies. So here comes the area frequency response characteristics. It plays an important role to bring back the frequency here. And finally, if secondary controls also are not capable of bringing them up to the national frequency of 50 hertz, then the tertiary control has to be there. So it is that means tertiary control is it's a additional generating capacity. So that has to be now. If we talk about the today's aspect, so it is about the battery storage system, etc. So it is can support the tertiary control there. So it's so how the very small frequency change can demand a small incremental power demand. Okay, so if there is a 0.03 hertz of frequency deviation, so there will be a 9.9 megawatt. If we take a 660 megawatt generating station, so if a generating station capacity is 660 megawatt and it experiences a 0.03 hertz of frequency difference, so it has to generate additional 9.9 megawatt, or it has to lose this 10 megawatt of generations. So this may be through the terminology used is free governor mode or restricted governor mode as operations. I told you in the I mentioned in two previous slides that one passing through 00, that is the free governor mode operation, and with a ripple of a deadband of plus minus 0.03. So this is a restricted governor mode operations. So if the frequency deviation is more than plus minus 0.03 hertz, means about exceeding this deadband, then there will be a additional generation of 10 megawatt, or there shall be the load reduction of 10 megawatt automatically. This is how the power system's frequency control works in an area. So multiple control area, that is a different methodology. Now you see that as we are talking about that integrations or the renewable energies. Now because of all of our works or research works or development works or innovation has to address what are the problems we are facing in day to day. So this is a recent incident. The disturbance happened on 11th August 2022 on northern region grid, where a solar generation loss around 6,000 megawatt happened, and how it affected all other regions, or all, that is the the concern of integrations of the solar renewable energies. So this is 11th August. The YB phase-to-phase fault occurred on 220 kV, one transmission lines, Badla Clean Solar Jodhpur line. Okay. So what happens that almost all the renewable energy station connected at this transmission line dropped their generation. So it covered Bhadla 1, Bhadla 2, Fatehgarh, Bikaner, all those things. Okay. Yeah, I'm in need of some. Yeah. So, it dropped their solar energy. They dropped their generations. The third effect gone to due to this sudden generation drop, over voltage in the transmission network at Rajasthan Renewable Energy Complex was also observed, and many 660 kV lines and 220 kV lines to RE station tripped due to over voltage, and it leads to total RE energy generation drop of approximately 6157 megawatt. Out of that, 5,800 megawatt solar and 350 megawatt wind. So finally, all these disturbance led to load shedding of approximately 400 megawatt in UP, 200 megawatt in Punjab, and 150 megawatt in Haryana control area. And on this DFDT protections. So rate of change of frequencies was very high under this event, and the entire all those regions has to do the mandatory load shedding all these areas. So this is a so we'll show you. I will show you that how it what are the backgrounds, why it has affected the other regions. So now to address these situations, how to come out of these kinds of situation, because tomorrow we are going to have the 62% of your non-fossil based generation, which do not have the primary response or primary frequency response characteristics. It generates only the active power. Okay. So how by controlling the active and reactive power we can come out of these situations? How the improvement in the flexible operations of the already existing generating systems, coal generating systems or gas fired, etc., has to be operate so that these disturbance can be mitigated. So in the black line here, the black line is that normal operating curve of any fossil-based power generating station. And for the flexible operations, we need it's a very high ramp rate, high your ramp up rate and high ramp down rate to support these kinds of disturbance on the grid. So we have to shift from black operating line to the red operating line. So it's not an easy task because it involves a lot of changes in the equipment. It involves a lot of change in the monitoring and control systems. It requires a lot of change in the load dispatch centers. Regional load dispatch centers also monitor and predict the load. So that's why I told that the load forecasting and predicting, that becomes most important to. So a lot of works are being done on and still are being done to address this for this grid managements towards smart grid managements. So now that there are some fundamentals here, then only we will be able to analyze the situations that our main for a rotating machines, the main electrical power is from these equations. Okay, you know that it is dependent on the damping constants or the damping torque for the machines. So when that machines get connected to the grid, the composite inertia, of which is called also the power systems inertia, that also become combined with the machines inertia, and finally if there is an imbalance, so it leads to the instability in the grid. This normally in the steady state, this the power generation and the loads are balanced and maintain the frequency. If there is a change in the power imbalance, mainly if the rotor angle changed, then it is the power imbalance gets absorbed either by change in the kinetic energy of the machines or by change in the load due to the change in the frequency. These are the methodology how to stabilize the frequencies. All of us are aware that how the grid inertia are related with the machines on the grid. So it is governed by the swing equations, and active power delivered by the machines is related to the your rotor angle, and frequency is nothing but that your rate of change of the your rotor angle. So what does this AGC does this with respect to this? It AGC is nothing but you're predicting the load generation, load demand, and accordingly taking the corrective actions before it happens. So the earlier days AGC was only to first detect and then take the corrective actions. Now the AGC concept has, after the development of artificial intelligence and load forecasting, AGC is modified that predicting the load and taking the corrective actions before it happens, just before it happens on the grid. So the lot of works are being carried out on these, and from the experimental basis, some of the power stations in the northern regions has tested it, but still now across the grid, across all regions, it is not yet implemented. So we are planning, the ministry is planning to implement for that to address the smart grid. So so now there are two frequency control approaches being taken. One is that your synchronous algorithm, another is that desynchronized asynchronous algorithm. So for the most practical purpose, this is decentralized asynchronous algorithm is being used because of there in the synchronous algorithm there are the loopholes in the system delay, which is practical, and that has been addressed in this decentralized asynchronous algorithm, and in most practical purpose this is being followed. So as I told that our minimum frequency or nadir value that is 49.5, and quasi steady state frequency it is 49.8, and area control error it has to be set 4%, not more than that. So these are the approaches towards the smart grid because the final objective of the smart grid, as I told, is the quality power, stability of power, and integrations of various energy sources. So this to have an idea of how your generating stations affects the system inertias. Okay, so in a 900 megawatt per hertz is much lower compared to the system of Western interconnections in US. In India, it is around 20,000 megawatt per hertz. Okay, so that is the damping constant, we call it. Okay, as you have seen that in the US it is the 20,000 megawatt hertz, and in India it is coming as 9,000 megawatt per hertz. So our grid is much prone or can be easily perturbed by any deviations or any disturbances in the power generating companies' sources. As you know that all the generating stations, like if it is a solar, then it is highly unpredictable. If it is a hydro, little bit predictable within a definite period. If it is a battery storage, we do not have that much huge number of battery storage supporting systems. So mainly our power systems, the stability is determined by the fossil fuel fired only. So another is that the area frequency response characteristics. This is, as I told, that this is from one region to another regions under tertiary or secondary controls. Okay, so it is the determining the area frequency response is purely a statistical methodology. It depends on the power system, and it is a time invariant functions. Okay, so we cannot have that fixed area frequency response characteristics for every region similar at every instant. It depends on the power system size, its a frequency at the start of the incident, generator loading, losses, distance of the generators from the point of losses, load compositions, number of generators in service at the time of the incident, type of generation, governor actions, time of day of season, and interconnections with the neighboring grid or control area. So you then understand that it is very, very complicated things to determine all those things on practical. So it is being monitored on real-time basis, and it has to be calculated on real-time basis to find out that what is the AFRC at this moment. This is the, as I was telling about this control area concept, is that this is the northeastern region, eastern region, northern, western, southern region. So area control error is being calculated by your actual net interchange, scheduled net interchange, your frequency bias coefficients, and actual system frequency, with all those things. Okay, so if we are able to monitor or control, measure that always what is the area control error, then only it is possible to accommodate all the other power systems, power generating resources. So this is the control area concepts. Just I will tell you the effect of these. So in a northern region load for a particular day, I have taken a reference. It was 47,168 megawatt on 12/10/2017, and operating frequency was 49.98 hertz. Suppose a 700 megawatt losses on the load loss happens, okay, or the generation loss happens, then if we assume that the grid load varies at 1.5% of every 1% change in frequency, then the damping constants of the northern region comes about your 1394 megawatt per hertz. And if not a single generating station in on free governor mode operation, the grid will have a very low system stiffness, and the frequency is only controlled by these damping constant. And so what will the frequency deviation under this instance is a drop in frequency by 0.5 hertz. So 0.5 hertz drop is a catastrophic change in the grid frequency. So if all the TGs, now if we can see that all the generating station in that control area are on pre-governed mode operation, that means no dead band, with all the machines having 5% rule, then your the area frequency response characteristics comes as your 0.035, and your beta factor becomes your, which is called the area frequency response factor, that is your 19,000 megawatt per hertz. So from the because this is as I told, this is a time variant. It's every second it is being not second, even every millisecond it is being calculated. So under these conditions, when such disturbance happened, the northern regions, the area AFRC range was 312 to 1075. Southern region, it was 575 to 1515. So you see that from region to region, how it is varying. So whether this northern region can support the southern region, can be supported by the southern region. So all being decided and decision taken automatically by the combined effect of all the characteristics of the smart grid, whether it is being supported by your renewable energies or fossil-fueled energies. So these kinds of decisions has to be integrated with the smart grids. So if we take about a pure fossil-based power generating station, we see that the response of the fossil-based power generating station is dependent at which operating load it is at that instance of disturbance. So if we take about consider an IEEE dynamic frequency response model of the rotating machines, it is found that the power output of HP, IP, and LP turbines at 100% rated conditions, contributing to around 37%, 29%, and 33% of total power output, respectively. So as the load decreases on the machines, that means frequency rising, okay, on the grid frequency rising, then contributions of the LP turbine in total power output decreases, while that of HP and IP turbines increases. Similarly, if the machine itself operate at a 30% load, means at lower load, where the losses are much more on the machines. Okay, so in that case, your HP contribution become 42, IP 30, and LP 27. So that means that why I have shown these figures, that the frequency, it's a dynamic frequency response model. The smart grid must have a model predictive analysis of all the machines operating on the grid, so that a real smart grid operation can be achieved. From that model, you see that the machine is basically a third order model, a turbo generator, So there, if we analyze, uh, that when there is no dead band, that is free governor mode operation, the maximum frequency change at 30% load is 0.0072. The maximum frequency change when the machine operating at 100% load is 0.0075. That means the peak frequency at lower load is lesser compared to the peak frequencies at higher load, and so the stabilizations is little bit faster. And if it is a machines on restricted governor with a group mode, you see that the peak frequency is still much lesser compared to the without dead band, and the balance characteristics remains the same. So it is an isolated machines, means if the machine is the only one. If it is a two area frequency response characteristics, if we analyze, then we see that this blue line is your frequency change in area 1, and this red line is your frequency change in your area 2. Okay, for a state load change, maybe suppose, as I told, that every 0.03 hertz immediately 10 megawatt plus or 10 megawatt minus. So that is a state load change on that machine. So on that so under that circumstances, the frequency response characteristics of each control area changes drastically, and if the disturbance is taken care happened in frequency area 1, then area 2 can support it. Okay, that means that your area 2 has to either draw some power or has to inject some power to area 2 from area 1. So this is a ideally tuned response of your steam turbine generator. So you see that within almost 35 seconds, the system frequency gets stabilized. So if we remember the first slides where I had shown that secondary frequency response has to be within 5 to 30 seconds, okay, to bring back the frequency. So here you see that actually, practically, it is taking around 35 seconds to stabilize the frequency. So there are different frequency stabilization techniques. Is the flat frequency control, flat tie line control, or tie line bias controls. So all those things are available here for the frequency stabilizations. So now how the AGC help in such instances. So AGC, it functions like that the regional load dispatch center, which monitors your all the generating stations. So it gives a demand set point to the AGC system at the RLDC. Then RLDC through IEC 104 protocol, it gives through the remote terminal unit, it gives the input to the every generating stations at the plant level or the station level AGC circuit, and then it controls controls the load at the individual machine levels. So this slide is more vividly has shown how detailed it controls. So this is the control area. For example, one control area this is. So this control area, there are a number of suppose the end generating station are being connected with that particular control area, and every unit or every generating station has its own control systems. So I have taken reference from the Northern Region Load Dispatch Center. The scheme, this has been tested at NTPC, one of the power station in Dadri, this scheme, and it has been found operating and controlling the grid frequencies successfully. This was the pilot projects there, and based on this, the more and more replica or the same control philosophy has been adopted for other station also. So NLDC, Northern Region Load Dispatch Center, it through router firewall, it gives that at the plant level what is the actual generation requirement. So that goes to the DCS, that goes to the generating station, and that is being catering power to that particular control area. So this is the scheme how AGC can stabilize the power grid. This is how the area control error I have shown also. The same thing has been implemented in this slide also, that how the area control error is being controlled, and calculated. So based on that setup, so we have found that this integration time constant is around 80 seconds under that instability event on the grid. The small signal proportional time constant is found to be 0.5 second. Large signal proportional time constant, that is also found 0.5 second. But regulation limits was plus minus 50 megawatt under AGC. Okay, and we are able to achieve that. And this ramp rate, whether ramp down or ramp up rate, that is 10 megawatt per minute, that also has been achieved. So this is one of the techniques of this AGC. So how in the plant level the AGC is being implemented. So this is the AGC unit. This block, it interacts with your load dispatch center. So this is AGC RTO unit at the plant level with particle swarm algorithm here being used for prediction, and it takes that input from the plant control also, and takes the set points from RLDC, and that what is the schedule generation and what is the AGC generation. So both are being compared, and based on that, the unit maximum load generation set point and minimum load generation set point are being set automatically under unit capability, and accordingly it controls the turbine and the boiler. So this is the complete stabilization techniques, and it is a proven technique. So there is another mechanism I also talked about, that is for smart grid, is that demand side managements. Okay, so one is that generation side managements, that is a frequency control technique of various methodologies, area control, etc., AGC, etc. And now how the demand side managements. So actual demand sides, that is very unpredictable, because we don't know that at what time what load will be there. Though it is every 15 minutes time block, some quantum of generation schedule is being evolved. Okay, but that always doesn't work perfectly, because the unplanned demand also comes. So in that case, that the immediate or fast response to the grid the solar generations or the renewable hydro generations, that has to be taken, or the battery storage systems, that has to be taken as a backup. But if it happens at night, so obviously there is no PV generations. So uh, all those concerns are already there. So that that this PV generation, it doesn't have any inertia. As I told also, the more and more renewable energies penetrate to the grid, the lesser and lesser become the grid stiffness. That means that any small disturbance, load disturbance, frequency disturbance on the grid can perturb to a larger disturbance on the country-wise grid. Okay, so then so as we are working towards that smart grid, okay, so the PV generation also has, or the wind-based generation has also to behave like a fossil-based generation with respect to your group characteristics, so that the support to the power systems inertia is achieved. So that is the idea behind the generations of the synthetic droop or the virtual droop characteristics, which is when nowadays many inverters are being for a large scale, it is still under R&D. For small rating inverters, it is being tested, but not for very large scale. Applying the synthetic inertias or the virtual inertias to support the power system inertia is being worked upon. This another big challenges to the RE integration to the grid is that active and reactive power component in the grid that the grid demands. Okay, for the distribution generating units, which comprises of various types, the low voltage distribution network has to limit the harmonics and not exceeding the voltage regulation criteria as defined in EN 50160 and IEEE 1547 standard. So whether we design the inverter or whether we design the power system network microgrid, okay, in that case also these aspects needs to be taken care. But as I told that for small scale it is being tested, and but for large scale inverter like in a utilities scale, it is still under R&D, and the learned people like you, there are a lot of scope to work on that field, so that it helps, because these are the fundamental components for a smart grid managements. If a lot of work are being at present are done, but still a lot of work are yet to be done to support or stabilize the grid. So we talk about that the another methodology is that controlling the active and reactive power, okay, towards smart grid. Okay, the beauty of this reactive power is that it is can be either generated or absorbed by purely that converter. Okay, and it has no limit. So you know that reactive power, it maintains your voltage difference, and active power, it is purely it is controlled by the frequency. Okay, so reactive power maintains the voltage difference in the transmitter network and the active power is purely it controlled by the frequency, or the active power controls the frequencies. So that for that PV based generations, or for these wind generations, so the role of the active powers become very, very important in stabilizing the grid. This is that the all of you knows that how it is methodologies. As I told that normally in all such cases we use the voltage source inverter. So in either we can implement the droop control through active or reactive current, or we may control the reactive power, active power through the power angle, and reactive power by the voltage. Two methodologies, both are available in the market, but as I told, it is very less limited to the large scale inverter, means the higher rating in utility scale. This has been still the implementations of the various methodologies are still yet to be done. The major challenge are for the wind and solar, it's the non-controllable variabilities. Okay, so you don't know that how to control the generations there because of the technology limitations. There are partial unpredictability. This is, you don't know that it is mostly dependent on the weather. So the weather forecasting and the predicting the weather. So that's why that the digital twin model of the power systems will help in minimizing these unpredictabilities, and the location dependence, because obviously the wind and solar, whatever in the Gujarat, it's not applicable for the West Bengal or for the Delhi or from other state. So these are that, it's a location dependencies, the generations. Okay. So non-controllable variabilities are, this is the, it's a moment-to-moment time scale has to be monitored on the, in addition to the prediction or weather forecasting. The variability impacts since it causes the fluctuation in the grid voltage and frequencies. And but compared to the conventional power network, the frequency balance between generation and load is simply very simple compared to the. It's not that simple also, as lot of technologies are available there. So here, when the frequency up, you reduce the load. When frequency going down, you increase the load. So that type of load frequency control methodology is already available. But for renewable energies, such load frequency control methodology is yet to be proven in the market or in the power systems. So because, as I told, that the renewable, there is active power is being controlled by the frequencies, okay, or the power angle. So renewable energies, it doesn't contribute to the frequency control. This is a big difficulties in designing. So that is the originations of the virtual inertia or the synthetic frequency. Sometimes it is called the 50.2 hertz problem, because whenever the frequency becomes 50.2, so that time it becomes totally uncontrollable. You don't know what happens to the power system. So better you disconnect the sources under those conditions, because it may raise a cascading effect on the power systems. Because how the cascading effect happens, that whenever there is a drop in the renewable, in the that 11th August incident, what I had mentioned in that, finally Haryana, Rajasthan and Delhi, all those regions, there is there was sufficient power cut or load shedding was there. So that is the result of the cascading effect. Actual point of origin of the disturbance is Rajasthan, and then the drop in the around 6,000 megawatt renewable and solar energies, including hydro, that has created a DFDT. So that is a great deal of unpredictable disturbance in the power systems. So the smart grid has to address all those incidents. So the next methodology to address this is that electrical energy storage. So the benefits are that power quality and stability, frequency regulation, spinning reserves, and load following and ramping capabilities. So power quality and stability, because as we told that it supports your voltage stability. It reduces the harmonics caused by your exorbitant uncontrolled variability of RE generation. Frequency regulation, of course, is moment-to-moment monitoring and variabilities in the RE generation output. That is also can be addressed. But as I told, for large-scale requirement, it is still to be worked upon or not proven still now. But by 2030, since the renewable energies generation will be around 62%, amounting to 500 gigahertz. So a lot of products based on the recent innovations has to be there in the market for the application. So partial unpredictability that I told already, that is forecasting followed by your advanced unit commitment with stochastic factors. So that is application of AI/ML tools help here. There are methods, as I told, the physical and statistical method. Statistical method is purely an artificial intelligence based support, and physical methods, it requires the actual modeling of the systems. It is modeling of the generating system, modeling of the forecasting, physical modeling of the forecasting methods. So disadvantage is that these are very sensitive to the systematic error. If one model becomes erroneous, then subsequent interconnect all models give your incorrect information. So that is the disadvantage of the physical model. Statistical modeling, it is that is based on your artificial intelligence. It is a highly accurate model because it's purely a mathematical model, which till now it is a black box model, but some gray box model is also available or can be derived gray box model also. And it is it's a highly consistent, because already we are having historical data which can parameterize the model and tuning of the model. So of course very special knowledge is required for statistical modeling of the power systems. As I have shown that a simple steam generator model is a third order model. So the entire power system comprises of steam generating system, PV system, wind generation system, your hydel system. So everything has to be modeled there to accurately predict or forecasting. So, but it's possible. It's highly possible, and so people or learned people like you can easily work upon those modeling and help in the industries in predicting accurately in stabilizing the grid. The fourth methodology is that grid demand response managing. So it's a good solution to ease the impact. Okay, so it helps in the power system flexibility. It helps in improving the grid stiffness by load shifting, by demand side balancing. So these are the methods, demand response methods, which also helps in stabilizing the grid. Uh, there shall be in the, as I earlier also told, that fast frequency response. That is the need of the hour. While we are talking about the smart grid, first frequency response is only available or only possible by the renewable energies, because all rotating machines is having its own system inertia, and together all generating station, the total system inertia is the summations of individual machines inertia. So and that is a slow process. As I told, that from a two area with each capacity of more than 10,000, I have shown the analysis. So it took 35 seconds to stabilize the frequency. Okay, so 35 seconds is too long in power systems. Okay, it has to be within 1 second. And the grid demand is that you stabilize the frequency within 1 second, but as on date it takes around 35 seconds area wise. But maybe in a particular control area, depending on the size of those control area, it varies from 5 to 30 seconds, based on the control areas capacity, control areas locations, the interconnections of other control areas, etc. So FFR is the need of the hour, which can only be supported by the renewable energies. So now most of the renewable energies we talk about is that the solar PV. Okay. Now there are to address this or to have this FFR, there are different algorithms working on the solar systems. So this is a power limiting control algorithm, or we call it PLC algorithm. So where based on that your demand, you can extend or you can raise your maximum power point of to support the grid. Uh, this FFR is under such conditions is nothing. This FFR is determined only by the additional active power injected by these solar generating station, responding to an additional mega power demands, supplementary signals in that solar control systems. Okay, so mainly the your inverter converter, they take a major role in this FFR. Okay, so this is one algorithm. The second algorithm is the ramp rate control algorithm, or PRRC algorithm. So here it's the similar to the PLC, but here for fast actions, the rate of change of that demand, okay, that acts as a feed forward signal to the inverter or converters to modify the MPPP algorithms there. Okay, so this is called your power ramp rate control. Another is that power reserve control algorithm. This is this power reserve control algorithm that is also very useful under such circumstances where it's the power reserve level. If you see this diagram, okay, that the control functionality The special case, it is dynamically changed based on the demand on the grid. So the MPPP algorithm is also accordingly modified dynamically. So this is the third methods, and this is a simple how any of these three methods can be implemented in a VSI with a digital voltage controller. This is a practical schematic of but not for very large scale utility, as I already told that this is for a microgrid. This is working, but when those microgrid will be connected to the main power systems, a lot of other factors also need to be considered. The instance on 11th August that in my first slide I had shown, that it was on large scale. Okay, so what happened that you have seen where all those these type of algorithms that to take care of that sudden load change, sudden frequency change has not been taken care, because that is not available still on some more and more research is going on those respect to apply in the practical aspects. So this is as I told, that this is the virtual inertias, how the advanced control strategies can make the inverter fed renewable energy system with a virtual inertia. That is nothing but that we call it that synthetic droop characteristics. Synthetic droop characteristics or virtual inertia is nothing but the inertia replicating the inertial response of the rotating machines, because this is the only factor which determines the stiffness of the grid, which determines the stability of the grid with respect to the voltage, with respect to the frequency, phase, harmonics, etc. So this is one methodology. In that event, which created a cascading effect on the northern region, so that is not applying the virtual inertia on that converter. Okay, so that is the effect of not applying this. Okay, so here a synthetic you see that different renewable energies are integrated, wind, then PV, lot of then energy storage, etc. So there is a inverter controls, and here virtual inertia is a synthetic program. So that is being added based on the grid frequency, which supports the actual power system inertias to maintain the grid stability. So this is the most modern technique using synthetic inertias, and I hope you people will be the right person to work on more and more on this, and that have a fruitful solutions towards smart grid. So the in short, the standard solutions for the smart grid will be data acquisition, process graphics, alarm management, data archiving, report generation. Energy management comprises of optimization of power production, power purchasing, energy storage and demand response, protection from high microgrid demand changes, management of energy flow and voltage regulation at the point of common coupling. Electrical controls, it's a breaker control and interfacing with IEDs. Load shedding, voltage controls with generator bar controls, transformer tap changer control, capacitor bank control, grid synchronization. So all aspects has to be there, and this is the expectation from a smart grid. So now a little bit about that, how we apply a 3D digital twin to solve these smart grid managements. So as I told, that the 3D digital twin is nothing but this 3D interactive virtual representation of the real world entities and processes synchronized at a specified frequency and fidelity. Okay. So it is basically digital twin. It comprises of the combinations of IT, OT, and ET. IT, OT, and ET. Okay. So this OT is the physical entity. Your ET is that engineering technologies, different your digital models of that actual machineries. So this is a virtual entity, and your service is that IT, how it helps in managing the smart grid. So it prevents vulnerable situations that would result from static measures, continuous decision in changing situations, and trustworthiness in operation of the systems. So all this together gives customer, because for what we are doing this, our objective is to give a quality and stability power to the nation. Okay. So the trustworthiness is above all. People should believe us. People should have confidence on us. So that is the trustworthiness in operation of the entire smart grid systems. So how it works? So it gives the asset managements and reliabilities. It gives the plant maintenance independent of its type, whether it is a solar, whether it is a. I'm in mid of some meeting. Yeah, no. So the plant maintenance, document management, planning and scheduling, simulation, safety and risk assessment. I talked about that, cybersecurity. So that is also addressed. The mobile role-based work packages for engineering, safety, operation, and maintenance. It's an application of AR, VR, means augmented reality and virtual reality, because sitting in the control room, you can visualize what is happening in that plant, and what is the operating status of those plant, if there any problem or not, whether any problem is going to come in the next 1 year, the prediction, forecasting. So all those are there in augmented reality and virtual reality. So for a fossil fuel fired systems, it is a boiler control and optimizations are there. And of course, the most important part is that physical and statistical modeling. That slide I have shown you, that is the mathematical and thermal process modeling and data historian for forecasting or predictive modeling. So these are the application of the digital twin in the smart grid. So it's purely a data-driven EIML based predictive model and resilient model also at the same time, where your ANN, IMC implements the artificial neural network, internal model-based control, model predictive control, dynamic matrix control. All those things are integrated there to generate a white box, black box, or gray box model, which will be having the ability of simulation and predicting and forecasting. So these are so the simple examples of the digital twin for power monitoring in a smart grid. So this is the energy optimization and management. So it leads to the energy accounting and monitoring in the live systems, opportunity generation and evaluation in live systems on real-time basis, means every seconds it is being of course for the grid frequency, it operates on the milliseconds. So that a special hardware is already there and applied. Transmission network model managements across operation and planning. So protection of data managements, streamlined renewable integration analysis using GIS data there are many companies, one, they are working on that based on the satellite imaging, or they analyze the data uh, with a statistical model, that feasibility, the prediction, forecasting, everything. Okay. Data managements for integrated T&D analysis, distribution planning model creation, and synchronization with GIS, DMS, and MDM data. Fault prediction and detection method based on the digital twin model. It enables the operators to predict the possible future state and provide solutions in time before the power system's failure or emergency occurs. That is the beauty of this digital twin. Dynamic digital mirroring, that is also another feature. It reflects the system status in real time, and data of remote terminal units and phasor measurement unit, or we call it PMU and RTU combinations, which advanced sensors gets integrated with the digital twin database and then used for the real-time prediction, simulation prediction, and fast system analysis, and gives that the management's feedback for taking control before some event or disturbance happened in a smart grid systems. Okay. So online dynamic security assessment, I told that it is based on that physical or statistical model. Both are possible. It takes care of your including your cyber security, that your failure rate analysis also it predicts. So now people do not have to calculate everything on your screen if we apply the digital twin here. The major is that fault prediction and detection, dynamic digital mirroring, already I have spoken. And the another important is the self-learning and machine learning algorithm. This is being combined to make this system trustworthiness, because ultimately that is the customer's requirement. Okay. So this is a one case study, that is a intelligent demand forecast. It was being done by a company called Visionize. I have taken the reference from our joint work with them. So it is a project called Intelligent Demand Forecast. The problem statement is that electrical distribution company must account for coincident peaks in summer or winter months from the electric generation corporations. Okay. Now, to reduce the cost of such peaks, utility distributors also run load control events by cutting electrical loads. But that is load shedding is not the solutions. Okay. So we worked on that how the digital twin and helps in forecasting and predicting these. So that ultimate gain from this project are focusing the increasing the revenue and reducing the cost, because if we reduce the cost, it is a benefit to the end user customers, and if we increase the revenue, so it helps in running the business. So it is a win-win situation for the organization as well as for the customers. Okay. So both are the two constraints or criteria based on which the model has been worked out. Okay, and it's purely based on AI/ML, and accurate prediction up to the 95% confidence level has been achieved with these. Okay, so that means we achieved that trustworthiness here. Okay. So the time to analyze this success, the project is 3 to 6 months post deployment, and we found that cost to buy a power is reduced increase in revenue, less power outages on the customer side, operational cost is reduced, and how many peaks currently avoided. So that is the idea behind these, to help in smart uh, grid managements. And it is the whatever I have talked about, the technical aspects, this is the recent advancement. Some of these I told that it is in a very in microgrid, for small rating of solar plant, it has been tested, but on utility scale it is yet to be applied. So my request to all learned person here present in these presentations, because you are the right person, you have the right resources and right knowledge also, because to give some lights, throw some lights on these areas, so that industry get benefit out of your research work on these fields. So that is all about, and thank you very much for your patience listening me. These are the reference, a few of the reference I have taken while presenting this, is that with visualize what work has been for the load forecasting and prediction, then some publications on modeling of steam turbine, then from IEEE publication, first bus transfer, so area frequency response, etc. So thank you very much.
Thank you, sir. Thank you, sir. Sir, such a
you,
knowledgeable
sir.
session we had, sir. So I'll request the participants if they have any thing to ask. The participants, you have any questions to ask?
Good afternoon, sir.
Yeah, good afternoon.
Sir, when Rajasthan solar frequency increases, as you discussed, to
Yeah,
50.2 hertz, which tripped the other region plant,
yeah.
the DFDT operation at that case, sir, should open the GCB of the other plants also, because
Yeah,
uh,
yeah. You
and
are
the
correct. Yeah, I
uh,
understood.
and the plant also goes to islanding mode. So
Yeah,
I am asking the what is the settings for that, sir, DFDT for frequency range, so that we can
yeah.
safely island.
Actually, frequency did not rise to 50.2 hertz. This problem is named or the characterized in the industry as 50.2 hertz problem. Okay, this type of disturbance is called as a 50.2 hertz problem, though the frequency has not reached 50.2 hertz. Before that, DFDT operated. Now, at every region, there are DFDT settings are there. Okay, northern region, so the grid coordinations are they give that settings to each power generating station depending on their control area. Not all machines in any control area has identical DFDT. Then the entire country will be on blackout mode. So to prevent that, every unit in every control area have varying DFDT settings. So those areas where this in Rajasthan disturbance created load shedding in Haryana, Rajasthan, and Delhi, all those. So they have all their DFDT settings differently. So that's why the disturbance limited to these units only, these control areas only, not have much more cascaded effect on other control areas. So there are the list of settings for each generating stations where the values are there. I am not able to recollect all those because there are a numerous number of generating station. So it varies little bit to prevent the blackout in country wise.
Thank
And
you, sir. Thank you.
islanding mode, as I told, that your those units should have come to islanding mode in, but this is more, practically it has been seen that as I have referred one my publications are fast bus transfer systems. Okay, So when the machine comes on islanding mode, the local frequency, it rises abruptly. It becomes almost, it rise to 53 hertz because it has gone in islanding mode. Okay. And it has come up, the local frequency means that at the plant level frequency, it goes to around 53 hertz. Now, if we analyze the frequency spectrum and in the fast bus transfer system, the window of this from station bus to the unit bus, okay, because when it comes to the islanding mode, all the drives or the power sources comes to the unit bus. So from station bus to unit bus, the frequency window setting is hardly 4 hertz or 2 hertz or 2.5 hertz like this. But under these conditions, the rate of change of DFDT becomes so high because suddenly the machine was on grid, which is having an inertia constant, means that it is facing a stiffness of the grid, and suddenly you withdraw that stiffness, and that means machine suddenly becomes free, and it
Means,
speed.
sir, it is running on speed mode, sir, or in load mode.
It is still on megawatt control. Okay, it's still not speed control. So at the time of incidence, it was on megawatt control. But once it comes to the just islanding happens, the first thing happens that disconnecting the station and unit. So whenever it comes to the unit, so what happens that direct your all the generator terminal voltage, it appears on all the auxiliaries drives, and it experiences high frequency that time because it's a just after disconnecting it from megawatt load control to it comes to the frequency control or speed control. And because of the sudden withdrawal of load, due to the inertia of the machines, it rises to the almost 53 hertz. So if this frequency response you expand in Taylor series, you will find that earlier it was only on the first term of the Taylor series. Okay, that was affecting based on that IEEE. You set that frequency window. Okay, but later in my work, I found that it is the second term contributing like anything. So that second term contributes to the DFDT, okay, in the local level. Okay, so that's why in the fast bus transfer system, that another factor has to be introduced there in addition to the flat frequency window to the second factor is that DFDT also. Okay, to the detrimental effect, if we don't do it, all your rotating machines connected on your unit bus, okay, that experience a very high electromagnetic torque, and which can damage all your bearings, pedestal, your coupling between driven equipment and drive. So this is the fact why it is being difficult to control. Ideally it should control, but practically it nevers, until and unless these kinds of protections. And now in India, hardly 2 or 3 power stations have introduced this in the bus transfer system, the second factor in the Taylor series.
Thank you, sir.
Thank you, sir. Do we have any other person? Any other questions? Thank you, sir. It was a knowledgeable session, and we are really happy to say that we have participants not only from the faculty, from academic group, but we are also having person from attending participants from the industry. So it was really a knowledgeable session, sir. Thank you, sir. Sir, dear participants, so one of the most biggest frontiers in electrical engineering today is the development and implementation of smart grid technology. It is fueled by the global demand for greener technology and alternative fuels. environmental friendly smart grid technology has the ability to stimulate stagnant economics as well as change the way power is delivered to electricity consumers around the world. So we really shared Mr. Shumanta Basu, our eminent speaker, shared a lot of case studies with us, and it was a really a knowledgeable session, sir. So, sir, this is just a token of appreciation from our college, Dr.B.C.Roy Engineering Group of Institutions, sir. I'd like to share.
Madam, I have one more question, madam. Can I ask?
Yes, sir. Yes, sir. Please, kindly.
Sir, my I want to ask you one more question. How digital automation and interconnectivity is done on smart grid in case of data server failure due to overburden of SQL or VN server?
Yeah. So for that, now you must be aware of the terminologies on the disaster management systems. Okay. So for these, till now, uh, the digitalization, the complete digitalizations of our power system has not taken place till now. Okay, there are a lot of people are working on that. Even the POSOCO recently, the name has changed as a Grid Control of India. As I told that before, during COVID time and this, while switching off all the uh, these lighting loads from the grid. Okay, so there are simulation study has been done before we go. They give go ahead for these. So there are partial digitalization happen. And regarding your DNS server or this data server, obviously, if one place is being damaged by any reason, whether it is a earthquake, whether it is a flood, or whether there is always a secondary systems available. Okay, in another
Sir, I mean,
geography.
a parallel redundant system is available or not for that case?
Yes, a parallel redundant system is available. First and second is that there is a concept of DMZ, and it's called the initially it is a concept originated from the U.S. Army. It is called the demilitarization zone. Okay, so that to prevent any intruder attack on all those server. Okay, so two kinds of attack may happen. Okay, for disaster may happen either cyber attack or by natural disaster. So the backup is already for the natural disaster. The backup is there in another place. So, but that is not to be discussed. Place not to be discussed in public forum. And for that cyber attack also to prevent, there are DMZ implemented so to prevent any intruder attacks there. But
Thank you, sir.
but still digitalization is yet to be done for 100%. So that's why I told that the application of 3D digital twin, that your modeling of the power systems, not that simple mathematical modeling, is that accurate modeling of your thermal system, your renewable systems. So now the discrete way many works are being done across the globe, but in concretely in way the all integrations of all those concepts and giving 100% solutions. So that is the one case study what I had shown. There it has been tried to work upon all those things, that load forecasting and prediction.
Thank you, sir.
Thank you, sir. Thank you, Mr. Dibendu Chakraborty. Uh, so it's time for us for a small token of appreciation from Dr. B.C.Roy Group of Institutions, sir.
Yeah, thank you very much.
Sir, just a minute. Sir, is it visible to you, sir?
Yeah, it's
Hello.
visible to me. Yeah, it's
Okay.
visible. Thank you for
Thank you, sir. Thank you, sir. So it was a great platform for us to share your knowledge. Sir, you shared your knowledge. Thanks a lot, sir.
okay.
Thank you, sir. Thanks for joining us, sir.
Yeah.
Thank you.
Let me now disconnect and thank you to your principal, your head of the department, and as a convener, Dr. Kamalika, you especially, and all the participants for carefully, patiently listening me. And I'm not a learned person like all people like you. You are all the pioneer in these fields. I shared only my experience and practical aspects on all those things, and hope you people will be working for the future, for the betterment of our country, and uh, we are working for our nation. Whether you or we, me, or every one of us are working for the development of our nation. Nation first.
Yes.
Thank you all.
Thank you, sir.
Yeah. Thank you.
Thank you for joining us, sir. Now this is a small information for the participants we are having today. The feedback link is shared. It's mandatory. It's mandatory to fill up the feedback form. The feedback form link is also shared in the FDP group. Thanks, participants, for joining us. We have the next session tomorrow, day 2 session tomorrow at 11 o'clock. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thanks for joining. The next session will be tomorrow at 11 o'clock. We will have Dr. Debashish Dey from Energy Institute, Bangalore. The feedback link of today's session is already posted in the group. Kindly fill up.